Everyone says quantum physics is mysterious, strange, impossible to understand, counterintuitive. They're right. But here's the thing. Nobody really understands quantum mechanics. Not the way they'd like to. But I can tell you how it works. That's actually very simple. Let me show you. In everyday life, everything makes sense. You throw a rock, it follows a path. A ball rolls off a table, falls to the ground. A car turns right, it doesn't go left. Objects exist in definite places. They move at definite speeds. A thing is either here or there, not both. That's common sense. And in the world of atoms, it's completely wrong. At small scales, things don't work this way at all. Electrons, photons, atoms, they don't behave like anything you know. Newton thought light was made of particles. Then we discovered it behaves like a wave. Then we found that light sometimes behaves like a particle after all. Same story for electrons. First particle, then wave behavior. So we gave up. It's like neither. To understand this, imagine 3 experiments. First, bullets. A machine gun sprays bullets through 2 holes in a wall. A detector behind measures where they land. Close hole 2, you get a pattern. Close hole 1, another pattern. Open both, the 2 patterns add up. Classical physics. Second, water waves. Waves go through 2 holes. They meet on the other side. Peak meets peak, they reinforce. Peak meets trough, they cancel. Result, stripes. Bright, dark, interference. Third, electrons. An electron gun, 2 slits, a detector. What do you see? Stripes, just like water waves. Now things get strange. The 2-slit experiment. Pay attention. This is the most important experiment in the world. Everything strange about quantum mechanics is right here. Turn down the electron gun. Make it fire very slowly, 1 electron at a time. You hear clicks from the detector. Click, click, click. Every click sounds exactly the same. Same loudness, same everything. No half clicks, no quarter clicks. Either 1 complete electron arrives or nothing arrives. Electrons don't come in pieces. They arrive whole, in lumps, indivisible lumps. So here's the natural question. Which slit did this electron go through? Perfectly reasonable question, right? The electron is a thing, a particle, a chunk of matter. It doesn't split in half. It must go through 1 slit or the other. Let's call this proposition A. Each electron goes through either slit 1 or slit 2. Sounds obvious, must be true. But now watch what happens. Let the experiment run, 1 electron at a time. Click, click, click. Slowly building up a pattern on the detector screen. And the pattern you get? Stripes. The same interference pattern you got with water waves. Stop right there. Think about what this means. If each electron goes through only 1 slit, what is it interfering with? Think carefully. 1 electron goes through, arrives at the screen. Then another electron goes through, arrives at the screen. 1 at a time. Minutes apart if you want. Each electron is completely alone. There's nothing else to interfere with. Yet somehow you still get the interference pattern, the striped pattern. How? Let's test proposition A carefully. Close slit 2 completely. Fire electrons. You get a certain distribution. Most electrons land opposite slit 1, fewer at the sides, a single hump. Call this pattern 1. Now close slit 1 instead. Open slit 2. Fire electrons. You get pattern 2, a hump opposite slit 2. Now open both slits. If proposition A is true, if each electron really goes through one slit or the other, then the result should just be pattern 1 plus pattern 2 added together. Some electrons go through slit 1, make pattern 1. Some go through slit 2, make pattern 2. Add them up. That's what you should get. That's not what you get. Look at the center point, equal distance from both slits. With both slits open, many electrons arrive there, a bright spot. But close slit 2, fewer electrons at that point. Wait, close slit 1 instead. Again, fewer electrons at that same point. So closing either slit actually increases the number arriving at certain spots and decreases it at others. How can closing a slit that the electron supposedly didn't go through change where it lands? At some places you get more than twice as many electrons with both slits open compared to having just one open. At other places you get almost none with both open, even though you got plenty with one open. This is interference, exactly like waves. But remember, the electrons arrive as particles, one whole lump at a time. Here's what makes it so puzzling. How does an electron going through slit 1 know whether slit 2 is open or closed? The mathematics is simple, though, beautifully simple. You calculate it exactly like water waves interfering, but the physical meaning, that's where it gets strange. Electrons arrive in lumps, like particles, but the probability of where they arrive is distributed like the intensity of a wave. Now let's do something that seems clever. You say, okay, I want to see what's really happening. I want to watch which slit each electron actually goes through. So you set up a strong light source behind the two slits. When an electron passes through a slit, it'll scatter some light. You'll see a little flash. That flash will tell you this electron went through slit 1, or this electron went through slit 2. Perfect plan. Let's do it. You run the experiment. Fire electrons one at a time. Watch carefully for light flashes. And here's exactly what you observe. Every single time you hear a click from the detector, meaning an electron arrived, you also see a flash of light, either near slit 1 or near slit 2. Never both at the same time. Never halfway between. Excellent. So proposition A was correct after all. Each electron really does go through one slit or the other. We can actually see it happening. We can watch which path it takes. Mystery solved then? Not quite. Not at all, actually. Look at the detector screen now. Look at the pattern of where electrons are landing. The striped interference pattern has completely disappeared. Instead, you just get two humps. Exactly what you'd expect from proposition A. Exactly what you'd get if you were shooting bullets. The pattern is simply pattern 1 plus pattern 2 added together. No interference, no stripes, gone. When you watch which slit the electron goes through, the interference pattern vanishes. When you don't watch, it comes back. Your observation has changed the experimental result. But hold on. Maybe the problem is that the light is disturbing the electrons. Photons are hitting the electrons, giving them little kicks, messing up their paths. That's why the interference disappears. Reasonable thought. So let's use dimmer light, more gentle, less disturbance. You turn down the intensity of the light source. At first nothing changes. Same results as before. You still see flashes. Pattern still shows no interference. But as you make the light dimmer and dimmer, something very interesting starts to happen. Sometimes you hear a click from the detector, electron arrived, but you don't see any flash of light at all. Why not? Where did the flash go? Here's why. Light doesn't come as a continuous wave. It comes in lumps too, particles called photons. When you dim the light source, you're not making each photon weaker. You're just sending out fewer photons per second. The light is getting sparser. So sometimes an electron goes through the slits and there simply wasn't a photon there at that moment to scatter off it. No photon, no flash, no information about which slit. Now you can divide your results into groups. Electrons where you saw a flash at slit 1. These electrons land in pattern 1. A hump opposite slit 1, no interference. Electrons where you saw a flash at slit 2. These electrons land in pattern 2. A hump opposite slit 2, no interference. Electrons where you saw no flash at all. These electrons show interference. The striped pattern is back. Stop and think about what this means. Really think about it. The electrons you detected, the ones that scattered a photon so you could see which slit they used, these behave like classical particles. They go through one slit, you can tell which one, and they make a simple pattern. No interference. The electrons you didn't detect, the ones that didn't happen to scatter a photon, these show interference. They make the striped pattern. This is not simply about physical disturbance. It's about information, about knowledge, about whether the path is distinguishable in principle. Try using even longer wavelength light now, red light instead of blue, or infrared, or radio waves with very long wavelengths. You try this. As the wavelength gets longer and longer, something remarkable happens. With very long wavelengths, the light doesn't pinpoint which slit very precisely anymore. Why not? Because when the wavelength becomes comparable to the distance between the slits, the light diffracts. It spreads out. A flash of light could have come from an electron at either slit. You can't tell for sure anymore. And here's the remarkable correlation. As soon as you lose the ability to distinguish which slit, as soon as the information becomes unreliable, the interference pattern starts coming back. Perfect distinguishability, no interference. No distinguishability at all, full interference. Partial distinguishability, partial interference. The correlation is exact, quantitative. The more information you have about which path, the less interference you see. This observation led to a fundamental principle, the uncertainty principle. For this particular experiment, you can state it like this. It is impossible to design any apparatus that will determine which hole the electron passes through without destroying the interference pattern in an essential way. If your apparatus is good enough to tell you which slit, the interference will be destroyed. If you see interference, your apparatus cannot tell you which slit. You cannot have both. This is not a technological limitation, not about needing better equipment. It's fundamental to nature. Here's the rule. If you can determine which slit, no interference. If there's interference, you cannot determine which slit. You can't have both. You might say, but it must really go through one or the other. We just don't know which. No, that's the mistake. Assume it goes through one, but we don't know. You predict two humps. Wrong answer. Nature doesn't work that way. The calculation is simple. For every possible route the electron can take, assign a complex number. A little clock face. Electron leaves the gun, goes to the screen. Thousands of possible routes. Through slit 1, through slit 2, even to Andromeda and back. Every route gets a clock. Follow the path. Clock hand spins. Calculate where it stops for each route. Add up all the clocks, all possible routes. The length of the total clock hand gives you the probability. Some clocks point the same direction, reinforce. Some point opposite, cancel. That's interference. Does the electron really explore all routes? Really go to Andromeda? I think so. That's what nature tells us. We know how to calculate. We get the right answer. But what it means, nobody understands the way they'd like to. What's an atom? Positive nucleus, negative electrons around it. Opposite charges attract. Why don't electrons fall in? Classically, they should. Moving electrons should radiate, lose energy, fall in, but they don't. Why? The uncertainty principle. Suppose the electron sat on the nucleus. You'd know exactly where it is. No uncertainty in position. But then momentum uncertainty must be very large. Large momentum means large kinetic energy, enough to break away. So the electron compromises, stays some distance away, some position uncertainty, some momentum uncertainty, some kinetic energy. Work this out, you get atomic radius of about half an angstrom, 1/10 of a meter. That's right. And the energy to pull an electron off hydrogen, about 14 electron volts. Matches experiment. The reason you don't fall through the floor is quantum mechanical. To squash atoms closer, you'd confine electrons to smaller space. By uncertainty principle, momentum would be higher energy. That resists compression. Let me show you why uncertainty is built into nature. Think about a wave train. Finite length. Try to count the waves. How many peaks? At the edges, the wave dies away. You're uncertain by about one wavelength. In quantum mechanics, wavelength determines momentum. So uncertainty in wavelength means uncertainty in momentum. And wave packet length, that's where the particle might be. Position uncertainty, put it together. Position uncertainty times momentum uncertainty is at least a fixed number. That's the uncertainty principle. From wave nature of matter, you cannot have a particle perfectly localized with perfectly definite wavelength. Not because of measurement, because of waves. Short wave packet, well localized, must contain many wavelengths, many momenta. Long wave packet, definite wavelength, spread out in space, poor localization. You cannot have both. An atom can only have certain definite energies, not any energy, specific values only. Why? Think of the electron wave confined in the atom. Like sound in an organ pipe, confined waves have definite frequencies, resonances. Same for electrons. Confined to the atom, the wave can only have certain frequencies, certain energies. Lowest energy, ground state. Higher energies, excited states. An atom in an excited state eventually drops to a lower state, radiates light. The light frequency, determined by energy difference. This explains atomic spectra, why atoms emit specific frequencies only. Take two electrons, scatter them off each other, put a detector at some angle. You detect an electron. Which electron, left or right? Can't tell. Electrons are identical. Because you can't tell, something strange happens. Two ways to get an electron in your detector. Left electrons scattered toward you, or right electrons scattered toward you. Cannot distinguish these. So amplitudes interfere, just like two-slit experiment. For electrons, when you exchange which goes where, interfering amplitude has minus sign. For some particles, alpha particles, plus sign. Why? Has to do with spin. Electrons have spin 1/2. Alpha particles spin 0. Half integer spin particles interfere with minus sign when exchanged. Integer spin particles interfere with plus sign. deep fact about nature, enormous consequences. Why matter has structure. Why you can't put all electrons in same place. Why periodic table works. Things on small scale behave nothing like things on large scale. Not like waves, not like particles, like something else. No everyday experience. We have a precise way to calculate. Mathematics is simple. The problem is interpretation. What does it mean? What's really happening? Nobody agrees on that. But we know when you cannot distinguish alternative roots, add amplitudes, then square. When you can distinguish, even if you don't look, add probabilities directly. That rule explains everything we observe. Observation matters. Whether you can, in principle, determine which root changes the result. Not because you disturb things, because distinguishability determines interference. Uncertainty principle is fundamental. Position and momentum cannot both have definite values. Not that we don't know them, they don't have them. Quantum probability is different from classical. Classical probability reflects ignorance. Quantum probability is built into nature. Strange? Yes. Counterintuitive? Absolutely. But it's how nature works, and every prediction we can test matches experiment to incredible precision. We don't understand it the way we'd like to, but we understand how to use it, and it works. That's physics.